Great. Thank you. Greetings, everyone. Good morning to those there in Montreal, and good afternoon, evening to our colleagues across the globe. So, again, I'm Paul DiGiacomo from NOAA Satellite Services and the Center for Satellite Applications and Research, Principal Science Advisor, but along with my colleagues, Rashmi and Aurelien, who you'll be hearing from shortly, we are the co-leads of CEOS Coast. And Mary Beth, let's go to the next slide, please. COAST is an acronym, and you could see it at the top. It's for the Coastal Observations, Coastal Ocean Observations Application, Coastal Observations Application Services and Tools, the acronym. And we are a brand new CEOS virtual constellation. We've been a CEOS standing team, ad hoc team for several years, but this past April in Tokyo at the CEOS SIP meeting, we became a full-blown standing CEOS body, virtual constellation. We're very happy about that, and I'm happy just to tell you a little bit about that today. Thank you to our GRIS colleagues for the ability to quickly speak to you, but more so this broader session. And thank you, Misako and Christo, our colleagues at the CEOS SST virtual constellation, for helping make this link. And it's very exciting right now. I won't go into extensive detail, but I think all of us know how important coastal zones are, sites of tremendous productivity, societal importance, from food security, commerce, and transportation. That's where the majority of the global population lives, within close proximity of coastal zones. And as a result, they're also subject to these tremendous changes and stressing and forcing that's going on in coastal regions right now. And so that's what we're focused on, is really trying to understand these coastal regions as a system, not from just an aquatic or terrestrial or an atmosphere, but from an integrated system perspective, and looking across that land, sea, atmosphere boundary, coupled with the social science perspective, which is very important as well. You see at the bottom, we have 6 pilot themes. So we're focusing on land impacts to sea and vice versa, looking at oceanographic processes, bathymetry, shoreline mapping, flooding, inundation, and then also in terms of what's going from the watersheds out into the sea, into the coastal receiving waters, loadings of sediment, turbidity, nutrients, and leading to processes such as coastal eutrophication, hypoxia, other important things. Most recently, we've added there, as you see, blue carbon, coastal blue carbon as a theme, and looking at coastal habitat mapping, so wetlands like salt marshes and seagrass beds, and working with other colleagues, particularly JAXA and CEOS for mangroves, and just to understand again how these come together. And we're leveraging our other wonderful CEOS virtual constellations. And for purposes of this group, obviously the Sea Surface Temperature virtual constellation, and then the partnership with GRIST, of course, but likewise out there, ocean color, sea surface height, etc. We have 6 pilot regions. You see those on the map, and where there's already extensive interest and activities underway. We're looking in the Bay of Bengal, state of Odisha in India, west coast of Africa, Chesapeake Bay in the US, the Mar de la Plata in South America, and then also Pacific, small island nations, large ocean states, and likewise for the Caribbean. We're in the process of adding an Arctic polar region site, and so we're interested in speaking about that. And you'll hear much more details, I think, but one of the opportunities is, how do we integrate with science teams and with GRIST and SSTVC to leverage all the wonderful work you're doing there, particularly make new and improved products. And for example, one opportunity that's come our way, and we look forward to discussing, is part of GCOS, the Global Climate Observing System, their most recent implementation plan from 2022, and this was brought to us by the CEOS Climate Working Group, was there's the need for development of new biogeochemistry products, but likewise developing products for variables such as temperature, turbidity, chlorophyll, color dissolved organic matter within 1 kilometer of the coast, particularly to address estuaries. And so the last thing I'll say is that this is a common theme we're hearing from all of our users and stakeholders, They want to get as close to the coast as possible for the aquatic parameters. They want the highest resolution possible, not just 1 kilometer, but 10 meters, 100 meters, and going down to 10 meters and then beyond, particularly 1 meter for shoreline mapping and bathymetry. And so I think we have an exciting opportunity to work together in that regard. And so happy to kick off the session. And with that, hand it over to colleagues Misako and Christo. Thank you all.
Hi, do we just carry on?
Yep, Christo, I think you guys are up next on the agenda that I'm looking at. Merrie, Beth, correct me if I'm wrong, but introduction to the CEOS SST virtual constellation. But Merrie, Beth, or Rashmi, correct me if I'm mistaken.
Nope, that's correct. This is Erica in the room. Christo, you are free to present now.
Okay, thanks. I was just kicked out. I was wondering what was happening. Let's see. Right, you can see my screen?
Yes, it's perfect.
Yes, we have you, Christo.
Okay, great stuff. So, quick recap of the SSTVC. I thought, let me just make sure I can. Oh, there we go. I thought I would just go back to this. Has been in the news recently, Earthrise, and why we're looking back at the Earth and how we were always looking upwards and outward and trying to reach out into space. And having that view brought us back to our host and how vulnerable we are and how it's boundaryless and what we can see. So Jorge reminded me of this sometime recently, and I thought I'd just bring it up again just to orient us on why we're doing this. So CEOS, just a brief kind of little history or something or relevance, was established to coordinate, harmonize Earth observations between different agencies around the world. But there's a strong GIRST overlap in terms of our community and what the focus was in interoperability, common data formats, intercalibration of instruments, common validation, intercomparison of products, all words that we bandy about quite regularly at GIRST meetings. And this is a strong CEOS focus, so it's quite natural for us to have a strong presence there. And it's a platform where the agencies, 34 space agency members and 30 associate members, of which CSIRO is one, contribute towards the advancement of space-based Earth observation science towards, understanding the Earth system better. And so the general structure, both CEOS Coast and us, the SSTVC, report to the Strategic Implementation Team Chair, and we coordinate space activities from the agencies, amongst different agencies, and then we leverage interagency collaboration and partnerships to address gaps in observation. This is squarely where Coast is going to be sitting now and collaborating with different virtual constellations and helping us to understand how to bring things, bring our observations together to understand systems more holistically in the different domains that was mentioned earlier. So our SSTVC members, 13 SSTVC members, here's all our names. I won't go through all of the names, save to welcome 3 new members, Facundo Eduard Godoy at CUNY and Natalia de Moraes Rudolph at INPI. And also Pallavi, she was a guest last year, was now fully fledged member from BOM, Australia. And the rest of us have been around for a little while. Right, so what's our role? We are the formal link between CEOS and GIRST. Essentially, I kind of always felt that SSTVC is GIRST and GIRST is the SSTVC. Because of the way we interact with the rest of CEOS, our whole community contributes to the SSTVC in the fact that our meeting is right at the end of our GIRST science team meetings. So us as a group, we benefit from all the information that we've received during the week, all the research that's been done, and that we can then collate this and contribute this to the SSTVC and then ultimately report this to CEOS and to our respective agencies. So GIRST really is the SSTVC. And to that effect, CIRS has completed an SST white paper, which is published as a deliverable for the SSTVC within CEOS. So we maintain a strong relationship between CEOS and CIRS, engagement between different nations, so fostering relationships, interagency, and what I did forget to mention earlier is that when you looked at all the agencies being represented in the SSTVC, it covers the whole globe. We've got members from South and North America, Europe, Asia, Africa, and Australia, which is very useful in terms of the perspective that we have and the needs that we have from different cultures and people around the world, not just the physical aspects, but also the social aspects that was mentioned earlier by Paul. So we work to assure long-term continuity of our measurements and synthesize the requirements for making these measurements, and then we support outreach, education, and development of new SST practitioners. So that is one of our priorities that I think we are not always highlighting strong enough during our meetings. And I know we're striving to build on this, but we might find some new avenues through COAST as well to strengthen our outreach. And we promote CIRS standards within the community, everybody working with SST, using the CIRS standards for data delivery and dissemination and also archiving. Advocate priority areas, promote the sharing of data, and then lastly, what we want to do now, or want to promote more strongly now, is collaborate with other CEOS virtual constellations through the COAST VC as a vehicle. So CIRS priorities that's come out from the last two meetings: improving level 4 product feature representation. A couple of presentations this week has highlighted that. We talked about broadening the outreach activities beyond academia. This was a strong point made in last year's meeting. And then fostering a close relationship with the other teams that I had mentioned before. So those kind of objectives is carried over. And so what are the limitations? Resolving upwelling and gradients, we've looked at that, and we've even looked at how gradients are resolved differently by different products. The declouding procedures, which have now been improved, as presented by Peter in his wonderful MODIS presentation. And the perception of the poor resolution in the COAST because of the use of level 4 products is actually quite pervasive in the non-EO specialist community. And we should not just be looking at kind of the long-term sea surface temperature signal as was presented by Chris earlier this week in quite a scary presentation with that sudden jump in 2016, but also to look at other representations or other signals of climate change, such as the frequency in changes in upwelling, the increase in HABs, and perhaps increase also in marine heat waves, or questioning how we're going to define it better. But the idea is that not to just look at the intrinsic SST signal, but also at derived signals from it, and how these products can represent it, how our products can represent it better, or integrate it with other virtual constellations to draw better conclusions. I spoke about broadening the user outreach. That there's a very diverse community interest in Earth observation these days. Just the level of publicity around that recent picture was an indication of how, with the uptake of social media, the increase in social media uptake and general communication, informal communication, the interest in space has grown again. And now with the advent of
Christo, I think you're muted. Okay.
Can you hear me?
Yes,
now
now
we can.
yes.
How long have I been muted?
A minute.
Oh, okay, a minute. All right, so we haven't lost too much. Let me get back here quickly. So, gather myself. Oh, I was talking about the broader user base and how it's important for us to be able to integrate with other products to address our users understand when they look at the environment. So now our user base has extended now from fishers, artisanal fishers, people within the fishing industry, aquaculture industry, the normal, usual environmental managers in governments, municipal or higher up. And each one of these users or stakeholders look at the data differently or required to be able to look at the data differently to understand their environment. And we need to interface with them to give them the products that they need so that they can make the decisions and so the products can be useful on a more immediate scale rather than just over the long-term planning, inter-annual or large-scale kind of government planning. And I think, again, Coast is one of the vehicles in which we can exploit relationships to be able to do that and play a bigger, more positive role in reaching a wider audience. All right, so just a quick example. I was talking about having, I was thinking about how we can reach artisanal fishers. I was talking about cell phones and having apps available, even a site that pushes data to them. Below is one of these NGOs who's developed an app that we support with information, and it's around looking at HAB impacts in the Benguela. HAB impacts can cause these crayfish walkouts when the oxygen in the water gets depleted, but understanding this, it also affects aquaculture, but I want to just, in the interest of time, move ahead to how we're going to integrate information. Understanding this is kind of combining what I have on the top left, sea surface temperature with wind overlay. So also CCMP, satellite-derived wind data. And below that, we have chlorophyll A concentration. And by combining the information from these three products, we'll be able to predict, or at least understand what's happening, and illustrated on the right, which is the physical conditions associated with the precursor to this HAB formation and the ultimate HAB impact on the coast. Now, these conditions manifest physically in terms of a front, which is firstly develops offshore. You have some phytoplankton growth associated with that, picked up in the chlorophyll A. The front translates towards the coast, and then further south, impacting in key areas where lobsters then ultimately get stranded in the surf zone. Now, the hydrodynamics can be modeled, but needs to be validated. And the high resolution sea surface temperature that we've been talking about in a week, but even 1 kilometer will go a long way towards validating this model of our region. But then also we need to be able to track what happens with the HAB once the bloom has developed. And to that effect, you'd need the chlorophyll A concentration for that validation, and then also use a drift model to calculate the movement of the HAB towards the coast. But it's an integration of different products to actually answer one question. Is a HAB developing? How big is it? How dangerous is it? Is it moving towards the coast? And what is the time frame towards the impact? How many days, hours do we have before we have to actually mobilize municipal or regional resources to move that valuable resource either offshore or harvest it in some way, and to protect the public against the impact of harvesting it themselves or actually being impacted by the other effects of algal bloom. And this might be a Benguela example, but of course we know this is happening in many of the other coastal upwelling systems and it could be extended further. Thank you. I think that is where I want to end, other than saying that we should encourage a strong presence in the new Coast VC. We should have a close relationship so that we can develop these tools that are already being used in various agencies. And I know in the States and Mediterranean, Oz, also in India, and Southern Africa also has their own decision support dissemination systems where we develop value-added products to actually help with resource preservation and responsible exploitation and other decisions that need to make around impacts of perhaps disastrous occurrences. Thank you. Hi, I'm not on mute anymore, am I?
Okay, thank you, Christo. We have to move on. Next up, we have a presentation on coastal observations through space, an emphasis on high-resolution SST, ongoing and future missions with high-resolution capability. And then we have Rashmi Sharma from ISRO, Aurelien Carbonniere from CNES, Andy Harris, and Jorge, who will be presenting in person. But we start off with Rashmi now.
Okay, thank you. Ratish, can you share the slides?
Can you see the slides on this? No.
No, not
for the
yet.
slides.
Share this screen. Share this screen.
Yeah,
Yes, no,
thanks.
we're good.
So a very warm greetings to all. Good morning, good afternoon, and good evening. Thank you, Paul, and thank you, Christo, setting the context of this special post-VC session. And before I begin this presentation, I would like to say a big thank you to the GRIST team, science team, for giving us this wonderful opportunity to have a special post session. So this is going to be a joint presentation by ISRO, CNES, NASA, and NOAA. And from the ISRO side, I'll be making the presentation, and then I'll hand it over to my other colleagues for them to talk about their missions and the upcoming satellite missions from their space agencies. So can you go to the next slide, Ratish? So from ISRO's side, we have to give 2 updates on 2 missions. So this is the first one is on INCOIS 3DS, which is in the geostationary orbit, and it was launched this year on 17th February with a 6-channel imager and 19-channel sounder. So the imager has a split thermal channel. So what you see in this figure on the top is that actually this mission, before I talk about the capabilities, I would just like to mention here that it is still in the in-orbit testing phase. And very soon the data from this mission will be made available to the global users. So what you see on the top figure is that this is an initial assessment of the black body temperature, which is quite stable for all the detectors. And also the temperature deviations are within the specifications. The maximum gradient that we have seen is going up to 0.6 degree Kelvin. So in all, the reason to show these 2 figures was just to tell that all the sensor instrument specifications are within the, we are meeting the specifications. And on the right, what you see is one of the sample images from this mission on the sea surface temperature. While the targeted spatial resolution for this mission is 4 kilometers, but the advantage is of a temporal domain with half-hourly data acquisition that will be available from this satellite. So, what we are looking forward is that the researchers and the scientists will be able to understand the diurnal variabilities in the sea surface temperature. Okay, so next slide, please, Ratish. So this is about our upcoming sea surface temperature mission, which is OceanSat 3A, and this is in the polar orbit. So the OceanSat series, it is the ISRO's series of ocean missions, and first launch from the ISRO on the OceanSat 3, which was in the November 2022, And this had a 13 band ocean color monitor along with 2 band sea surface temperature and KU band scatterometer to give you the ocean surface winds all from the same platform. But unfortunately, the sea surface temperature monitor on board the mission stopped functioning due to some in-orbit anomaly. But what we are looking forward is the follow-on mission, which is OceanSat 3A. The launch is scheduled in next year. So, and we will be having the opportunity to get the sea surface temperature at a resolution of 1.1 kilometer at Nadir at that kind of a spatial resolution. So this mission is going to give us a good, the sea surface temperature very near to the coast at a good spatial resolution, and also the expected sea surface temperature accuracy, which is expected is better than 0.8 to 0.9 degree Kelvin at the resolution of 1 kilometer. Towards this, what our colleagues have done is we have developed the retrieval algorithm, and this algorithm is basically the standard, the standard nonlinear sea surface temperature algorithm, which was proposed by Walter Newton. And this we have tested with the modest brightness temperature data as a proxy data. And what we have found that algorithm is working fine, and we are ready with the retrieval aspect. So as soon as the data,
I think we lost the internet connection. Can people online hear us from the room okay? Okay.
Yeah, we can
Yes,
hear
we
you
can.
well. We just
Okay.
lost Rashmi.
Okay. I think that was her last slide maybe. So I think the next person, we're just going to move over to our local. We will present locally here. So I hope you can see my slide now. And we have Andy Harris on stage. What? Oh, yes. Yes.
Yeah. So I think that what I'm going to talk about here really is what I think the GRIST community can particularly provide, guidance in terms of particularly the ultra high resolution SSTs. And so I'm just going to highlight a few, let's call them considerations. One of them, a lot of the examples would come from EcoStress, and basically I've not looked at EcoStress data, but David Wethy has, and he's provided a lot of information. And also there's a paper out here, which basically I've taken a number of these things from. One of the things that has been observed is essentially biases in the data. And so if there are any calibration experts in the room, hi, John, this is the sort of area which, we're talking about basically about a Kelvin offset in all of the channels. No, it didn't get, just for once, it didn't jump forwards. There we go. And the result of that is that you end up with actual biases in the SST as well of about a Kelvin. And you can see the sort of distribution, roughly sort of somewhere down here. This is a Hofmodel plot. So those biases are sort of pretty well distributed, fairly, I was going to say uniform biases in a way. And this propagates into the also, using the TESS algorithm means that they separate out emissivity and therefore estimate emissivity. And the emissivity estimates are also low, substantially low compared to what you'd expect from classic SST, in RT, TOV, and so on. That's what the red lines are, which is, I find it a bit odd. Because if the emissivity was low, if the retrieved emissivity was low, I would have thought that the end result of that would be that the SST would be high, because you have to scale up the SST if you're going to reduce the radiance. So I'm curious. I think part of this stems from essentially this separation of emissivity stuff comes from the fact that it's the test mission algorithm. Okay, but the thing is, hold that thought. But anyway, notwithstanding that, once you can apply some corrections, you do see some things in high resolution data like this, which, you know, here's some very nice AXPO VIIRS data, but you don't see these features here are well below the resolution resolving power of the VIIRS instrument. Fascinating filaments and so on. I mean, also I did mention at the very first slide that there is sort of a striping thing going on, and you can see this kind of pattern here, which is a consequence of the detector. So there's maybe a little bit of work to end up to remove some of that striping. Another great thing, of course, about having ultra high resolution is you can get all the way into very, very complex environments on the coast, estuarine environments and so on. So VIIRS has a bit of a stab at it, but, you know, then you hit the land temperature and everything gets messed up, whereas it's all very nicely delineated here. And of course, you've got all sorts of things going on in these bays, and mussels and other oysters and all sorts of things going on. So for aquaculture, this sort of information is invaluable. I mean, there's some use here, but essentially there's far more information available from that. Now, one of the things, as I said, that these are land surface temperature algorithms. It's a land surface temperature mission, so it's not too surprising. And so basically, we are sort of begging a little bit of extra coverage off the edge of the landmass to try and get the coasts in here. And so we have, because we have ultra high resolution, we end up with narrow swaths. Not really narrow. I mean, is it LSTMs? Maybe, they're getting up to 800 kilometers or something of that order, depending on the instrument. But there's also a vast amount of data at that resolution. And so we need multiple missions to get something close to what I would consider a daily revisit. And unfortunately, of course, in reality, the higher the resolution that you have, the quicker the processes change. So those nice features and filaments and so you saw in that image, they're not going to be there next day. They're going to be in a completely different location. And just to give you one last idea of what that actually looks like, this is 24 hours of 2 kilometer GOES 16 data. Okay. So we've got hourly motion. You can see hourly motion, substantial hourly motion in this, a 2 kilometer resolution. So what's it like at 50 meters? What revisit time that we said we'd like to get a day, but in reality, what would you really like? 10 minutes, 5 minutes? It's the size of the constellation you'd need to get that sort of revisit time. I'd say you want probably at least hourly, because if you take a look at what's going on in the Chesapeake Bay, you can see substantial signals in the temperature around the 24 hours as well. I mean, there's a fair bit of cloud, but you can definitely see it going up and down by, at least a few degrees. So maybe we need a lot of CubeSats or stuff to really get the full benefit of it. But I think probably right now it's going to be a case of persuading the agencies that run these instruments to provide us enough data to cover coastal areas and, extend the land mask out, or the coverage mask out for high resolution to, of order 100 kilometers would be nice if you want to capture strong upwelling events and things like that. And then you'd be able to do proper process studies, and then maybe you could justify the size of constellation that you'd really like in order to see what's going on the sub-daily cycle. Thanks, that's all I have.
Now over to you, Aurelien.
Yes, I guess it is my turn. So good morning, Montreal, and good morning, everyone. So Aurelien Carbonniere from CNES, and I have here, so I hope that everyone can listen to me easily. So there are a few slides to promote and to present you the Trishna mission, the upcoming Trishna mission. It is an ISRO CNES cooperation, and it is planned to be launched in 2 years' time, and to last 5 years. So hopefully, we hope that beginning of 2026 we will see we will able to see the Trishna launch. Trishna is really conceived as a real thermometer for the Earth. And you see that one of the two design drivers are the ecosystem stress and water use, and the second one is about coastal waters and inland waters. Its coverage is supposed to be global, and the performance will be based on the 3-day revisit, and the resolution will be quite precise, about 60 meters. It's about the combination between the visible thermal and also near infrared domains, because they are Trishna it will be based on and composed of 2 different instruments. So one in the thermal domain and the other one in the optical domain. So you see on the bottom of these slides the envisaged products, level 2 products, and one of them is about the land and sea surface temperatures. Ideally, for the land aspects, there is this daily evaporation products, which is also very quite expected by the research communities. And the next one, please. And you see, sorry, I just remain few minutes. You see that on the graph, if you can just put the other slide before the first one, sorry. Not this one. Yes, this one. Thanks. You see that on the diagram on the down below that Trishna is also conceived as a precursor for the future Copernicus mission, LSTM, and SBG NASA mission. So so the research communities are actually working towards this launch in 2026. So the next slide, please. Yes, well, this one is about, yes, to highlight again the fact that the two main objectives will be agriculture and coastal and continental hydrology. There are subsequent other objectives on urban, cryosphere, atmosphere, and solid earth. Below in the text below, you can see that there have been several meetings, quite important meetings, not only with ESA, but also at the national level, at the French level, with our research communities. There was one big meeting at the beginning of this year to really embrace all the research communities interested in the 2 main domains, let's say ecosystem stress and coastal and inland waters. And many different stakeholders were involved. And one key aspect of these meetings in particular was to really highlight the coastal challenges, then the fact that Trishna can really provide an added value in that objectives. So at the moment, at least on the French side, the research community is really working to better identify the gaps and needs regarding how Trishna can make a real contribution to coastal related challenges, not only in terms of sea surface temperatures, but also in terms of ocean color. Next one, please. So this is really to highlight that the cooperation between India and France is very active, of course, but it involves a lot of different laboratories and research centers. So and even on the Switzerland side, there is also a lab involved. So so yes, next, please. This one is really to highlight that Trishna is will provide I would say a thermal contribution to the study of the planet Earth, but at the same time there is also this altimetry mission which is called SWOT, which has been built across this partnership between CNES, NASA, and other agencies in the UK, for instance, and in Canada. And SWOT has been launched last 2022 at the end of the year 2022. You see that the very good combination between the two will be ideal to really inform the coastal environment. So we are really looking forward to gather and to and to combine altimetry and also physical parameters and biological parameters from the Trishna mission. And this is really to reflect that this combination will really help all of us to better assess the water cycle and the energy cycle as a whole. But yes, it will make a big contribution towards this understanding of the water cycle. Next one, please. And I think that's all for me. Thank you.
Thank you. Okay, we have Jorge up next. It's up to you.
Apologies for the delay. I just want to go over very quickly, a little bit of a perspective from NASA supporting COAST. We continue with the production of the level 4 multi-scale ultra-high resolution sea surface temperature data set. One of the, and Ed has already mentioned this, one of the accomplishments is we have now this high resolution data set, the software actually running on the cloud. So we're heading in that direction. And so hopefully we'll get some funding also to continue with the MUIR SST data. So one of the things that I think is important from our experiences with MUIR is, and I think this is going to be an issue, as we continue with the focus on ultra high resolution, is you see incredible differences in the MUIR data set when you go from periods of time where you have infrared data available to periods of time when you only have microwave data available. And this can happen very quickly, especially off the California coast. So I think one of the things we need to also look forward to is obviously the application of better cloud masking. But also I think one of the parameters that MUIR has, which I think is very beneficial, is allowing the users to know when there's actually infrared data available. And as we pursue further, the ultra high resolution component, for COAST, I think this is also a very important issue. Also, we need to make sure the users understand the quality of the data. And that's not always the same. That changes. So I think however we can improve, the issues of quality flags, that's going to be very important for COAST. Then also, I just want to go over very quickly, obviously MODIS, Terra, and Aqua are still giving very good data, but I think one thing, and there's been no final decision on this as far as I know, but one thing we need to also remember is, the MODIS, Terra, and Aqua are planned for decommissioning in the not too distant future. And they've been very, very important data sets in terms of providing high resolution SST data in coastal regions. So that's one thing we need to also plan for. And also we continue supporting VIIRS data set from SWAMI and MPP. So we do that also in collaboration with NOAA. We get both of those products at the JPL PODAC. AVHR, obviously we're planning to, that's going to be continued also. So that's another data set that provides high resolution data and specifically in coastal regions. The great thing about AVHR is obviously we have almost 40 years not almost. We have over 40 years of data from AVHR. So the calibration of this data set is really one of the most amazing, climate data records available. And it provides, again, continuing high resolution in coastal regions. And obviously plans for the future, sea surface temperature, very, very ultra high resolution, sub 1 kilometer resolution from eco stress, and also, plans for supporting Trishna. I just want to also say very quickly, with respect to eco stress, as a side note, in the work that David Withy is kind of leading, we are going to be supporting a postdoctoral student. And part of this will be obviously implementation of algorithms and also supporting the plan in terms of which is to get the EcoStress SST data set distributed as an official GRIS product, again, through the PRODAC. So if anybody has any possible candidates for a position, please let either David or myself know. And one of the things I also want to say, because we've had a lot of talks about the issue of the calibration and noise, and there are other experts in the room, but one of the things I want to say is on the positive side, when you're looking at in coastal regions, sub-mesoscale and mesoscale fronts and all that, yes, you might have more noise, but you also have a larger signal. So that's one of the things I think in terms of application of these eco stress and Trishna and coastal regions that we can still be very positive about. Thank you.
Okay, thank you, Jorge. And so next up, we have Prasanjit Dash from NOAA, who will present on the introduction of CEOS Coast Application Knowledge Hub case studies.
Perfect. Hello, everyone. My name is Prasanjit, co-affiliated with NOAA STAR and CSU CIRA, and I'm going to briefly introduce the CEOS Coast Application Knowledge Hub, or AKH. So AKH is a part of COAST, which is a VC, as Paul told. And the VC was spearheaded by Dr. Paul DiGiacomo from NOAA, and Dr. Rajkumar and Rashmi Sharma, who is online from ISRO, among other partners. I'm just a guy and happy to have my fingers on the AKH. Some of the long-standing members here may remember, since Paul is here, who supported our 2016 annual science team meeting in Washington, D.C. that CIRA had organized. So Application Knowledge Hub is designed to help assess the state of coastal areas and monitor events, primarily but not limited to using satellite data via some sort of web interface. So visualization is the key. If you cannot visualize something, you can't really fix it. And proper science visualization is key to any remote sensing application, which is what the AKS does here. As a reminder, the goal of AKH is to contribute to coastal safety, awareness, and possibly restoration efforts as well. So the use of word safety implies there is some perceived threat. The word cloud there, the word cloud there summarizes some of the events that threatens our existence on the coast, originating from various parts of the from the Earth system model, including human actions and also atmospheric effects. The image that you see there, I can't figure out the pointer. Yeah, there you go. The image you see there is a screenshot of the AKH online tool. And while the importance of being online is really obvious, or is there anyone who wants to know why being online is important? I guess no. Let's just focus on the word knowledge there. The word knowledge here refers to an actionable and interpretable summary of information. So you got data, you got information, and then the knowledge. For example, you have level 0 digital numbers or L1B data, brightness, temperatures, when you derive something like SST or chlorophyll that says something about the state of the ocean, that's information. And when you see something like El Nino or changing trends, etc., or HABs, those are examples of knowledge in this context. So this slide shows the overall concept of AKH, or Application Knowledge Hub. The coastal processes can be broadly classified under sea to land and land to sea, that capture the physical, the biological, and the ecological aspects of the coastal environments. So it's a little bit like what Andrea Pisano showed in Blue Ocean and Green Ocean, etc. The physical aspect can be captured with parameters like sea surface temperature, wind speed, inundation, geomorphology as well. Likewise, the water quality indicators, they can describe the biological and biogeochemical aspect of the coastal environment. On the right side, the infographics that implies that all this kind of data, they go into the system and generate specific analytics and visualization for coastal applications. And finally, they are shown somewhere in the web interface. That's the application part we call. Okay, now moving on to the infographic elements, coming from infographics to infographic elements. That is the type of data needed for such studies. This is a busy slide, and I really want you to remember everything in detail so we can discuss in the later. No, just kidding. Let's just focus on the main colors and also the headers. In blue, what we have is satellite data, meaning various ocean parameters, as well as composite images like false color, true color images. The non-satellite data, they fall into two categories, the curated category and also contextual. Curated means that the data have been acquired and kind of sub-selected a little bit, and they include information like storm tracks from IB tracks, NCI IB tracks, HAB locations from UNESCO HADAT, oil spill locations from NOAA RRR, and some more information. In light green, we have contextual information, meaning they are context to the study. Those include hydrology, social indicators, and land, and also land sea interface, like USGS coastal ecological coastal units and ecology data. Finally, in deep blue, we have high order derived information based on some sort of research generated either in-house or published literature. And we'll see a couple of examples of those as per the title of this presentation. Before that, very briefly on the technology part, without going into the details again. So this application has a complete client-side architecture. The raster tiling part is inspired by NOAA Ocean View that uses a modified version of ED, JPL MRF technology, meta raster format. The vector information, we typically use GeoJSON files, but for large vector, Mapbox vector tiling and Google Protobuf is used. Those are very efficient to handle large amount of vector data. On these blocks here, we see some of the map controls and map interactions, and also some scientific features that is available in the AKH. So from here, we'll stop describing, just see a couple of examples. The first one, the top image, is one of the time series plots from NDVC data. As you click on the station location here, further information about the station is also available in this table, and these are pretty fun to play with. They're interactive, and there is a pro tip tab here. So there's a whole bunch of operations like linear fitting, so you can have some fun there. The bottom image is LCLU land use classification image from US CCAP. They use Landsat 30-meter data. This is available for all of the US coasts, not globally yet, and we will also include whatever high resolution LCLU data is available in the future. Maybe Sentinel-2 is a good option. Okay, now we are switching to what I refer to as higher order information. This one shows a subaquatic vegetation SAV Habitat Suitability Index, HSI. The work is done by one of our colleagues, Rachel Lazaro. This is using VIRS data, sea surface temperature, chlorophyll, and some other water quality parameters for each year. And it's a high order product which ranges from 0 to 1, 1 being most suitable for the habitat, which is seagrass in this case, and 0 being least suitable. There is also a split functionality here to visually compare across different years. So just an example of this higher order information. If you want more information about this, please reach out. And this is an example of land loss and gain in the Mobjack Bay Area, again using Landsat data. The work is performed by our colleague Nikolai Neslin, and there is also a published paper on this if you're more interested. These are vector information. Oops, sorry. These are vector information, meaning that you can click on each point for further information. There's more to it. So, have some fun exploring this. Now, moving on to future projections, something like decades in advance. This is based on an external paper again. What it is showing is a projection on the left image, a projection to the year 2050 for episodic extreme events due to sea level rise. It's not mean sea level rise, it's episodic extreme events. And look at those vulnerable areas, mostly in the red dots. That is for RCP 4.5. If you're familiar with RCP, those are climatic pathways essentially. So yeah, this shows the vulnerability map. So if you are going to visit areas like Nova Scotia after this meeting, just make sure to come back before 2050. It's going to get rough. Okay, on the right side, we have similar. It's not included yet, but we'll also include the mean sea level rise from IPCC and NOAA reports. Okay, this slide shows the decadal trend rates in 4 different parameters. It's sea surface temperature, chlorophyll A, sea level anomaly, and wind speed. There is a 2-part paper that is under review for this work, so you'll see some more once they get accepted. But the trend detection is based on an integrated approach of spectral analysis, meaning using Fourier transform and continuous wavelet transform. That's what you see here for transform, continuous wavelet transform, to extract the periods that is necessary for the decomposition. So once you have the periods, let's say it's annual or 3-year, 4-year, whatever, that goes to a method called MSTL, multiple seasonal trend analysis, something like that. And then you decompose the signal to trends, seasonality, it could be multiple seasonality, and also the remainder of the noise partner. The point here is the trends are usually treated as linear, but for simplicity, and they work to some extent, but they are not linear, they are non-linear. This is the same example. Now you apply that thing on each individual grid cell, come up with the trend line, take the slope, and plot the map. So this is a sea surface temperature trend rate based on CCI 2.1. I didn't have access to version 3 ON that time. But anyway, very briefly, we see a lot of widespread warming here with some cold trends or trend rates. But this is one of those spectacular observations where there is cooling trend in otherwise warming area. And I think the good thing here is what we see here from observations matches well with the model, like Hartley model or something. So that's a good thing. At least the pattern matches, maybe not absolute values. Yeah, well, I think that's it. So we saw a few examples, and but there is much more to it. So I encourage you to explore on your own. We also have some more features on the horizon, like event maps or story maps, which will be interesting for individual events. In summary, the AKH will enable simultaneous displaying of a range of information useful for coastal studies. They're listed here. There was an alpha release last year, and the beta release will be sometime this year. In the future, we'll also do some machine learning kind of studies to analyze simultaneously heterogeneous data set to make some more meaning out of it. And yeah, that's it. There is also an user onboarding icon on the application. So once you are there, you don't have to listen to me or this talk. You just go through those steps, and that explains how to explore the page. That's it. Thank you very much.
Next up, we have Balaji B on coastal applications of SST, Ocean State Forecasting PFZ. So Balaji, if you turn on your camera.
Yeah. Am I audible? I wish to present from my side.
I can just present from the local room here, and then you just let me know.
Actually, okay. If possible, I will present from my side. I think, is it my screen or visible?
Okay, yeah.
Is it fine?
Yes, that's fine.
Yeah. Thank you very much. Thank you very much. Hello, good morning, everyone. Myself, Balaji from INCOIS. I am very much thankful for the opportunity. I am going to talk about the application of coastal SST. Mainly, INCOIS, Indian National Center for Ocean Information Services, provides a wide range of applications and services to a large group of communities like society, industry, academia. Many services are there. Here I am mainly focusing on the services which uses SST. So they are ocean state forecast that we assimilate the SST in the ocean models. From the improved initial condition, we are running the model in a forecast mode, which will give next 7 days ocean state information. That is one of the major service provided by the INCOIS. And the other service is potential fishing zone advisories. And one more service is coastal and marine environment. All these services uses sea surface temperature. I am from Ocean Modeling and Data Assimilation Group. Mainly, I am going to focus on the improvements in ocean state forecast with SST assimilation. So for this purpose, we are using a high resolution ocean model, ROMS, Regional Ocean Modeling System, which is operational at INCOIS. This provides ocean state information for Bay of Bengal, Arabian Sea, and Indian Ocean rim countries. I'm going to show the model domain and brief details of the model quickly. In this pre-model, there is no assimilation. So then we try to develop a assimilation scheme using LETKF and interface with the ROMS model. So this I name as LETKF ROMS. Whenever I say LETKF ROMS means ROMS with assimilation. Free ROMS means ROMS without any assimilation. In this system, we assimilate in situ temperature and salinity profiles from various in situ observation platforms like Argo, moored buoys, ship data, like that. Along with in situ profiles, we are assimilating level 3 track data of GHR SST. Here I am showing a typical web page of the ocean state forecast products which INCOIS is disseminating on a regular basis. So mainly we provide these for next 7 days at very 3-hourly or 6-hourly time resolution. The surface currents, surface temperature, and 20-degree isotherms, MLDs. The outputs from this forecast is further used in many other services of INCOIS, like search and rescue operation, where these currents information is used. So coming to this LETKF data assimilation scheme, we are categorizing the observations into 2 categories. One is assimilated observations, that is in situ temperature and salinity profile. and sea surface temperature. The non-assimilated variables are sea level anomaly, sea surface salinity, and currents. So in the right side, I am showing a typical distribution of in situ observations over a span of 1 year, which went into the system, which are assimilated. Yeah, on the other side, that is the SST track data, which is getting assimilated. So before going into the actual results of assimilation, I want to highlight the impact of SST assimilation. On the top corner, I am showing the model domain. It is Indian Ocean model covering the entire Indian Ocean from 30 east to 120 east, 30 south to 30 north along the north-south direction. So the top panel is observation count. That means on a daily basis, starting from September 2016 to February 2017, in the top panel, I am plotting the number of assimilated observations. So initially, I did not assimilate any SST observations. Then in November 18th onwards, I switched on the SST assimilation. Then I able to see a strong impact on correlation and RMSD. Here in the second row and third row of the first column, I am showing the domain averaged time series of correlation and RMSD of SST. Okay, so the red line indicates with assimilation and blue line indicates no assimilation. So by switching on the SST, I can see there is an improvement of around 0.1 correlation, and RMSD is more or less same. This is a domain averaged RMSE. The main and very exciting improvement is in the currents. Currents is an independent variable, but through the LETKF scheme where they have model error covariances influences, I am seeing improvement in the currents. So the improvement in currents, there is a reduction in RMSE, almost 5 centimeter per second. This is a sensitive experiment where I did not do much analysis. I just want to see how much the SST is causing the improvement. Then this is the actual result of 1 year of my run. Here I am showing a domain spatial correlation maps and spatial RMSD maps. The first column is, that is A and D, is with assimilation, and the second column is free ROMs. There is no assimilation. So we can see with SST assimilation, there is improvement in correlation in most of the regions along even the improvements are clearly seen in Bay of Bengal and Arabian Sea. The third column highlights the difference between correlation map of LETKF ROMs and free ROMs. So wherever there is a red color indicates improvement, and blue color indicates degradation. In the second row, it is a similar spatial map, whereas this is a RMSD. So here blue color indicates in the difference improvement. But here my main focus of this presentation is to give the importance of coastal SST. Actually, the accuracy of coastal SST compared to open ocean, it is less. And I'm not seeing much improvement in the head Bay of Bengal and along the Sri Lankan coast also. If you see these two regions, I will show the more comparisons with in situ observations in next slides. And in this slide, I want to show the impact of SST assimilation. SST we are assimilating at the surface, but there is an impact in the subsurface also, because in the LETKF scheme we kept as no vertical localization. So the improvements are immediately related to the deeper layers also. So here to highlight the impact of coastal SST, I chose two locations. One is at 15 north 90 east, another means slightly towards the head Bay of Bengal, that is 18 north. Why I choose? I have the data from these two locations. In the top row, I am plotting the time depth section of the temperature profile. from the observation. And the bottom panel is same time depth evaluation of temperature from LETKF ROMs. And the third column is the quality controlled observations. Actually, at 15 degrees, there are more quality controlled observations compared to 18 degree. And due to this, the model is not able to capture the variations which are seen in the 18 degree north, 90 east. So in the open ocean, the improvements are significant, whereas near the coastal regions, the improvements are marginal. This is a similar kind of analysis using the ADCPs, that is the current profile. I am showing the time depth evolution of currents from 4 different locations. Here I am taking 2 locations near the coast, that is Goa and Kadalur, and 2 locations from the open ocean. So this green color is Goa, the ADCP located on the Goa slope, and blue is on the Kadalur slope. The other red color.
Dr. Balaji, sorry to interrupt you, but
yes.
it would be better if you can make it fast, okay?
Yeah, sure, madam, sure. Yeah, here I want to highlight the improvements in coastal. The improvements are very less significant near the coastal ADCPs compared to open ocean. Yeah, I will quickly. So this is also a similar kind of comparison of currents from Tamil Nadu coast. See, the second panel is RMSD. I want to highlight this RMSD. In open ocean, the RMSDs are around 20 centimeter per second, whereas when it's coming to the near the coast, it is going beyond 40 centimeter per second. The next service I want to show is PFJet service using the SST data. This is also a regular service. We use the SST data and chlorophyll data and to provide the PFJet services. This is how we do. Like we take the AVHRR data of 1 kilometer and generate the coastal potential fishing zones, and this is disseminated by providing various information like the distribution, angle, location, where the fishermen need to go. So this is also a marine heat wave service. These are newly started services based on SST. Most of these depend on the accuracy of the coastal SST. Hello, thank you.
Thank you.
In between, there is a connection issue, I think. I'm sorry for that.
No worries. But yeah, just in the interest of time, we will go to the next presentation, and then the workshop will end with a discussion. So if you have a question, just write it down. But now we have Elyse Bonner, who will be presenting on SST and climate change, global warming, ecosystem health, chloral bleaching, and coastal pollution.
Hi, everyone. My name is Elyse Bonner, and I'm a CNES Marine Policy Fellow with NOAA CoastWatch. So today I'm here to present from the NOAA SST user perspective about NOAA SST user applications and advancement of NOAA SST for worldwide expectations. And here's a brief outline of my presentation today. So I'm going to talk about the background of CoastWatch, the SST working group report, a couple of NOAA SST applications, and highlights from the CoastWatch annual meeting and the SST user panel. And so CoastWatch is the interface between people and developers of satellite data, and it provides a platform for users to find, choose, access, and use global and regional satellite data for oceans, coast, and inland water applications. And so we prioritize working on these 6 objectives on the screen on the left, where we view and access data products. We have a portal where people can view and access data products, but we also have curated and monitored data sets available for our users. And as Christo mentioned, we are getting an increase of various users with levels of satellite experience. So we provide trainings and a learning portal on our website as well, so that anyone can learn how to use satellite data for their environmental applications. And so we're able to do this by partnering with our regional node managers across NOAA through various line offices, so the National Marine Fisheries Service and the Office of Atmospheric Research as well. So we have 5 regional nodes and 2 thematic nodes that all work together within CoastWatch to identify user needs and create satellite data products. And so, as Shakila mentioned earlier this week, the NESDIS SST working group was chartered in 2020 to establish and provide guidelines and documentation for the advancement of NESDIS SST to fulfill worldwide requirements. And so they released a report in 2022. This was the first report outlining what those advancements are. And so one thing I wanted to highlight is that the product suite, or one product in this report, was accepted into the NESDIS 5-year plan, which was released last December. And so another component of this report was a user survey that was sent out to about 300 individual contacts for NESDIS SST, and with about 112 responses. So I wanted to highlight a few of those important NOAA SST users in this report as well. So this was the aspirational SST product suite that was identified by the working group. So it's identified that it needs to be consistent routine products at level 2, 3, and 4, along with the maintained climate data record. It needs to be of global coverage, time period extending back to 1981, a minimum resolution of 0.05 degrees at level 4, and better at the coast, but also has to have consistent bias correction in historic satellite data and in situ data, as well as conform to GRIS file formats. And they want this product to be interoperable for NOAA CoastWatch and NCEI data servers. So one important fact in this aspirational product is that it has to be designed with consideration from key NOAA stakeholders. So as I mentioned, that report included a user survey. So I'm going to highlight 3 of NOAA's SST users on which 51. Yeah. Thank you. Sorry about that. So this is one SST user, which is NOAA's Coral Reef Watch. And so it's the only global early warning system for coral reef ecosystems. And it's important because it is mandated through the NOAA, the Coral Reef Conservation Act. So it's serving domestic and foreign governments and the U.S. Coral Reef Task Force. And so this product suite helps to monitor conditions causing coral bleaching, disease, and death. And as we know, that we just experienced the 4th global bleaching event happening. And so this is a global and regional product. And they've identified that SST is absolutely foundational for their product. So we want to be sure that we're ensuring to meet users' needs, such as Coral Reef Watch. The next SST application that I'm going to talk about is from the Western Pacific Regional Fishery Management Council, in which they are also mandated by the Magnuson-Stevens Fisheries Conservation and Management Act. And so they include SST in their annual stock assessment and fisheries evaluation reports. And so this is serving the Western Pacific region, and it summarizes fisheries performance and resource management in compliance with that act. So they incorporate SST and other satellite data in this report as well. And last, I want to talk about the NOAA Ocean Observations Viewer, formerly known as the Hurricane Viewer. But it serves users at NOAA, the Naval Oceanographic Office, the National Hurricane Center, and it provides a web-based portal where users can access satellite data, in situ data, and model data before, during, and after these hurricanes. So it's used to guide field operations and SST, among other satellite and in situ parameters are incorporated into this product as well. And so that brings us to 2024. So that user survey was sent out in 2020, and we wanted a chance to talk to our SST users again. So we had the 2024 CoastWatch annual meeting last month with about 134 registered attendees in person and online. And so at this meeting, we had a special session for SST where we gathered a few users to have a panel and discussion to highlight their needs. And this was co-facilitated by me and my colleague, Ron Vogel. So we had the CoastWatch annual meeting. We had 5 users ranging from coral reef monitoring applications, Vibrio infection risk, seascapes classifications, seagrass climate modeling, and estuary temperature history. So all of these users are using SST data for their coastal applications. And the topics that we discussed in that meeting were current SST data incorporated into their products, their SST spatial resolution needs. We talked about reprocessing SST data in the time period that's needed, near real time and delayed SST quality trade-offs, and we also discussed uncertainty and validation of these SST products. And so I'm just going to highlight a few things that we discussed and what came about this panel. So there is a strong need from our users for increased spatial resolution that's beyond 5 kilometers. And so our users in the Pacific Islands and those monitoring coral reefs are requesting a minimum of a 1 kilometer resolution. And so that's so that they can deploy monitoring and sampling resources when these events are occurring. And they also identified that if we could, in terms of prioritization, if we could downscale to the US coastal regions, it would be of great benefit for our SST users. And it might not be possible on a global scale, but if we can begin to create regional SST products at a higher resolution, to help monitoring of those small islands. But they are aware that with this increased resolution, we would also need increased land mass and improvements to that as well. And another term of prioritization, what we heard yesterday with Oceans and Fisheries from Environment Canada is that a 30-year time period is sufficient enough for these users. In our products, we mentioned going back the entire extent of the satellite record, but they just want to assess these ecosystem changes. So our climate scientists are satisfied if we prioritize for a 30-year time period and provide them with that data. All of our users are willing to wait for high quality, high accuracy SST information, but the users who are using SST as a public health risk assessment or an early warning indicator, they still need high accuracy, near real time SST data. So in that conversation, we also had to discuss the trade-offs between that. And so they're willing to accept that uncertainty as long as it's documented, and they have requirements to validate their products on their own, considering they're using it for public risk. So as long as it's documented, the uncertainty, they can incorporate that into their products on their own, and that's fine with them. They accept that. So that brings us to uncertainty and validation. So one user mentioned that they really want to have a better grasp of understanding the dynamic nature of regional bias changes, whether that's through maps or other modes. So what we realized is the products that we have available through NOAA STAR, such as IQUAM and SQUAM, it seems like they're not as available or accessible for our users. For some reason, they're not able to locate that information. So for CoastWatch, doing a better job of communicating where those products are and how they're able to access them. And so more information about uncertainty in those products on our data portal would be very beneficial for our users as well. And so in summary, for prioritization for SST and NOAA, a regional 1 kilometer SST product reprocessed back 30 years would be extremely beneficial for our users in the near term. But along with increased remote sensing resolution, there also has to be increased SST land mask improvements as well. And so we want to be sure that we are providing guidance and promotion of our SST quality validation products that STAR is creating on CoastWatch's data portal as well. And we want to keep having these conversations between users and developers to discuss ongoing product development and feasibility. Like Andy said, with increased resolution and increased temporal coverage, we want to make sure that our users understand what's even possible in the near term for their satellite applications. So as I mentioned, the SST products we identified in the NESDIS 5-year plan is funding dependent. So we want to ensure that in the meantime that we're meeting user needs and increasing our user engagement and communications during that time. So thank you. This work was done with Veronica Lance, the NOAA CoastWatch Program Manager and SST Lead.
Thank you, Elyse. And then we're going to, we are going to move over to Anne O'Carroll. Just pulling up her.
Hey, good morning, everybody. So my name is Anne O'Carroll from EUMETSAT. I'm the GRIS Science Team Chair. So first of all, I'd like to say thanks to the CEOS Coast team for putting this session together, and particularly for Rashmi for raising the idea in the first place and asking me to give a presentation today on coastal margins of the polar region. So this presentation is put together from a number of different GRIS Science Team members. It's based on really a lot of discussions that we've had over the last couple of years on high resolution SST, very high resolution SST, and coastal needs. I'm sorry there's not very many pictures, but it's kind of a gathering of thoughts and points. So I'll go through and just talk about GRIS needs and priorities to start with, and then go through some very high resolution sea surface temperature needs. I'll talk about Arctic and Antarctic challenges, and also mention the upcoming GRIS task team on coastal SST. So over the last kind of 2 to 3 years, we've had lots of discussion on coastal SST in GRIS meetings, and we've put various needs and priorities together. All that information is available through the last meetings notes and presentations on our webpage. So I'll go through a few of these points. There's quite a lot of overlap within some of them, but that just shows that, yeah, these are really kind of like priority needs and things that get talked about many times. So we would need evolutions at high latitudes for sea ice and coastal products. It's really important to have a focus on very high resolution sea surface temperature in coastal regions. This is really a strong priority for GRIS. A point that has been raised is the consistency between sea ice concentration and SST for level 2 and level 4 for infrared and microwave. A need is there now to incorporate sea ice surface temperature and SST in the products as the same domain. So we saw that that's now under discussion and ongoing within the GDS evolutions. There's a need for consistency and continuity of high latitude SST, marginal ice zones and the IST. So you're having really the consistency for SST products over the high latitudes and the marginal ice zones. And this includes both algorithms and product specifications. It's important to identify preparations and synergies from opportunities from the upcoming new missions, including the very high resolution sea surface temperature. And finally there, but not least, more CalVal and fiducial reference measurements at high latitudes are needed. So this slide just summarizes some of the discussions that we've had in advances in very high resolution sea surface temperature. So as we know, and we've seen this week, several new satellite missions with very high resolution are going to become available in the next few years. And this gives great opportunities and advances. But this also means that we need to prepare for it. So there are new opportunities for high resolution, coastal, polar SST, feature resolution and fronts, and synergies with other instruments and parameters. And this means that there'll be preparations and developments for SST from very high resolution, such as 100 meters. But this also means that developments are needed for retrieval, validation, and cloud masking. And this means that then we can lead to good representation of small-scale variability in coastal zones. Another highlight is that we would also need to define a new coastal SST product definition. So this would be both for level 2, level 3, and level 4 products. So I think that's something that's not yet really been thought about. Yeah, all of these new missions are giving great advances, but they also bring new challenges. So aspects such as complex coastlines, resolving the contrasts in these regions, and also the upcoming very high resolution missions. Many of them are based on the land requirements and not the ocean requirements. But we've seen some kind of presentations in previous meetings that this means that we would have higher noise and biases than the current SST user products and requirements. So that's something to think about. So a couple of recommendations there would be to reduce the noise and improve the calibration for the next generation of very high resolution missions. So we're thinking, 10 years plus there. But I think particularly within the CEOS activities, it will be important to coordinate the needs for that future generation. And in terms of the upcoming very high resolution missions, there's work to do to improve the SST algorithm techniques based on the mission that are coming next. Okay, so this slide just focuses a little bit more on the Arctic and challenges and questions. This is a little bit of a collection of thoughts. But yeah, an ongoing topic I'd already mentioned is that there need to be an update to the GRIS data specification to combine SST, marginal ice zone, and sea ice surface temperatures. It's important to progress on cloud masking and such as overflagging in coast and the frontal zones. Improvements are needed to high latitude cloud screening and quality control. Improvements to nighttime bias and uncertainties in particular. Thinking about sea ice and icebergs, and also thinking about temperature and algae in fjords affecting the aquaculture industry. It's clear that more CalVal and in situ measurements and FRM are needed. And there should also be intercomparisons and harmonization of high latitude satellite SST and sea ice surface temperature products. Okay, so this slide focuses a little bit on the Arctic from the ocean modelers' point of view. Thanks to Steiner for these points. So there's such as the case of fewer or no SSTs during the summer and nighttime. To increase the number of summer SSTs, daytime data are only filtered out between 10 and 2 o'clock during low wind speed from May to August. And another coastal issue for modelers, the temperature of the rivers with water from melting snow during spring. Since the temperature of the river water in the model is the closest water grid point, and during the melt season, the sea fjord water can be significantly warmer than the river. So a couple of needs there from the ocean modelers. And here's a few points on the Antarctic. So thanks to Bureau of Meteorology for these points. So evolutions in ocean ice coupled models need consistent SST and IST data over the Antarctic marginal sea ice zone. And challenges and questions, such as the warm bias in the southern hemisphere ocean models in summer, to assimilate IST to test improvements of summer melt tendency. The Antarctic coasts have low winds and variable ice in summer. The lack of nighttime summer SSTs, this is meaning mostly daytime over 6 meters per second are assimilated, and consideration of future microwave SST, including at higher resolution. Yeah, I think we used an very old slide set there, so we're missing a couple of slides. So we'll update it afterwards, but there was one slide on temporal needs, and I think mostly the point from that one was that with the new missions such as SIMA, then we'll get a frequent overpass time in the polar regions, and this will give us a much better revisit time for the microwave missions. And we also had a slide on the coastal SST task team. So this is in progress. So Emmanuelle Autret is coordinating the activities here. So we'll be setting up a new coastal SST task team to focus on some of these challenges. And I think Emmanuelle's up next to give a few thoughts. So in summary, we have GRIST high priorities on polar and coastal SST. There are new upcoming very high resolution missions giving great advances for coastal products. However, improved algorithms are needed to maintain the quality in terms of bias and uncertainty. We would request the next generation of very high resolution missions to improve the calibration and bias for the ocean applications. So I would see that as a core activity for the CEOS SST VC team in coordination with the CEOS coastal VC team. We would need to define a new product definition for coastal SST and to continue to evolve the GRIST data specification to combine SST and IST and improve consistency and product format. Okay, thanks.
Thank you, Anne. So next up we have Emmanuelle, who will be presenting on future high resolution SST in coastal regions. And also David Wethy.
Hello everyone, I'm Emmanuelle Autret. I work at IFREMER and I'm involved in the Trishna science team, especially on the activities, leading the activities of the science team in for the coastal and inland water applications.
And I'm David Wethy from the University of South Carolina, and I'm on the EcoStress science team involved in SST-related issues.
So we would like to give some additional elements, especially for the discussion and maybe for the panel discussion after the coffee break. As already mentioned by several presenters this morning, observations with resolution, with spatial resolution higher than 100 meters have been available for decades, for example, from the Landsat mission, and also since 2018 from the EcoStress mission. But those missions were primarily dedicated to land observations, even if they cover the coastal zone, and they also provide some L2 surface temperature product, but with the same algorithm than the algorithm that is used for the land observations. And as already mentioned too, three missions are coming up. The Trishna mission in 2026, the NASA SBG mission in 2027, and the Copernicus LSTM mission with 2 satellites, LSTM-A and LSTM-B, with a launch foreseen in 2029. Here you can see an example of surface temperature acquired by Landsat 9 off the coast of France, or the coast of Brittany. So many things about Trishna and EcoStress have already been presented during the last meetings with talks and posters presented by David or myself. So we would like to remind you the coverage, since we are talking about the coastal applications. So Here is the example of the acquisition mask from Trishna, from the Trishna mission. And thank you to the GRIS community to answer the question. Some of you, many of you have answered the questionnaire 2 years ago, and it allowed to extend areas that were not covered initially in the Trishna mission. So thanks. And so in green will be acquired the observations with 60-meter resolutions. And so all coastal waters up to 100 kilometers from the shore. And you can see on the right hand side panel the number of acquisition per 8-day cycle. So all full resolution data will be acquired from latitude below 60 degrees. And for high latitudes, only acquisitions with a 3-day revisit basis will be acquired to avoid very huge volumes due to the revisit at high latitudes. Initially, the 3 future missions are trying to harmonize all the acquisition masks and everything, but maybe recently David will show that there are some changes in the NASA HPG mission. So as mentioned by Anne, a new task team is going to be created, focusing on these high resolution observations. The objective is to address the specific challenges for the very high resolution observations, and for the existing missions and also for the upcoming missions. So the issues to be addressed will be first, I think, the identification and the collection of coastal in situ observations for the validation, since validations for global products, for global 1 kilometer products, are usually done by using drifting buoys or Argo floats, but we can't find many drifting buoys and floats close to the coast. For sure, a critical point are the masks, cloud, water, land, and ice masks. How to deal with the tides, and for example, in the files, should we give some information on tides and how? Of course, SST retrieval algorithms and geolocation validation, for example, as shown last year in the presentations. And of course, already presented by David or Andy, the problem of noise and stripping, for example. And we have to think also about the distribution, about the formats, and the GDS could be adapted. And also, I think we have to work on and to maybe to help the harmonization of the 3 future missions. And I think David has an example.
So I'm just going to highlight the differences with the between SBG and the other high resolution missions. Originally, there was an agreement to have the same high resolution acquisition mask for all 3 missions, but the NASA team has found that there are data bandwidth limitations, so they've been changing their acquisition mask. So currently, this is a mask from the beginning of June this year. There will be a 50-kilometer band on the coastal zone of most of the world, which differs now from the 100-kilometer band that is in the plan for Trishna and for LSTM. So this means there'll be less acquisition in the full width of the upwelling zones of the west coast of the Americas, the west coast of South Africa, and the Iberian zone of upwelling. Now, this is balanced against an increase in the amount of Arctic acquisitions. So they are planning on having complete acquisition of the Bering Sea, for instance, and a larger acquisition zone than is that's also planned in the Labrador Sea. So there's a trade-off between reduced acquisitions in upwelling zones, but greater acquisitions in the Arctic. So this means that instead of having daily acquisitions in a 100-kilometer wide zone around the coast of the world, there's going to be 2 out of 3 days for the zone that's between 50 and 100 kilometers. So that's just something we need to plan for. But it's possible that pressure from this group could push NASA into changing their high-resolution acquisition mask.
So, okay, thank you. That's it. And anyone interested in participating the activities done by the future task team is welcome. So please email me, and the group will be created in the coming weeks. Thank you.
Thank you. Thank you, Emmanuelle and David. We now have our last presentation on coastal biogeoprocesses and thermal fronts from Amala, who is online. Amala, I can share do you want to share your screen, or should I do it?
You could share it, and
Perfect.
I will say next for every slide, if that's okay.
Perfect. Yeah, that's fine. All right, you're good to go.
Okay, thank you very much for the invitation. So I'll try to be quick. So I'm interested, what we're interested in is trying to understand how SST is related to coastal biogeochemistry. And particularly, we start out by looking at upwelling zones, coastal upwelling zones. So when we have upwelling, we expect a cold SST. And at the same time, we expect nutrients to be upwelled, and we see a response in the biology. So shown here is, I think what I want to stress is that the response is very different depending on where we are in the ocean. So looking at the Arabian Sea here, so this is the onset of the monsoon, the summer monsoon, when we have southwest winds from the southwest. And you see that there's a very strong signal in the Arabian Sea of a coastal upwelling, but a very weak and almost indiscernible signal in the Bay of Bengal in the SST. Next. So this is showing us a region near the coast, a 100-kilometer wide region that we selected on both coasts around at the same latitude. And we looked at both wind stress and the change in SST over this annual cycle. And so with the start of the southwest monsoon, you can see that the wind stress in the Arabian Sea is much stronger. It's about twice as strong. But if you look at SST, you'll see that the signal or the drop in SST in the Arabian Sea is 10 times as strong as the Bay of Bengal within this 100-kilometer zone. So the question we're asking is what's happening? Why do we see a strong SST signal in one region and not in another region? How can we relate this to the physics? And if we can relate it to the physics, can we have a way to predictively, based on wind stress, come up with an estimate of how much upwelling we'll get and what the biological signal would be, or the biological response. So I just want to emphasize that the upwelling strength depends on the wind stress. So tau here is the wind stress and divided by the density, and F, which is the Coriolis parameter. Next. So here is what we see as the biological response. So once again, in this figure on the right top, you see the chlorophyll signal. You see a very strong response to the upwelling in the Arabian Sea, poor response in the Bay of Bengal, a 10-fold increase in chlorophyll in the Arabian Sea, and a 2-fold increase in the chlorophyll in the Bay of Bengal. If you look at the nutrient profile, so we looked at nutrient thinking maybe this would explain it. And of course, the nutrient is reflective partly of, the chlorophyll is reflective of the nutrient. So in the Arabian Sea, we have a lot more nutrient near the surface. compared to the Bay of Bengal. It's very strongly depleted at the surface, and there's a very strong gradient. But then you can say that that is because the upwelling is so strongly manifest in the Arabian Sea and not in the Bay of Bengal. Next. So what we are trying to do here is trying to relate the upwelling to the internal structure of the ocean. And this figure shows you a schematic of coastal upwelling. So when the wind blows on the top into the page, you see that cold water is upwelled at the coast. So the strength of the upwelling depends on the wind stress. But the question that we are asking here is, where does the water upwell from? If it upwells from very deep, then its signal is going to be colder. So it depends on two things: the strength of upwelling and the depth or the temperature of the water that's upwelled. So we can look at a balance between this upwelling strength, which is a wind-driven overturning, and the eddies, which are trying to rectify that front. And by looking at that balance, we can estimate the depth from which water is upwelled. So on the right, I have a source depth, an estimate for source depth. And it depends not only on the strength of the wind, but also on the stratification, or inversely to the stratification, which is N. So N is the vertical gradient of density. So the stronger the density gradient, the more shallow the depth from which it upwells. I can also find the density of the water that's upwelled, and that depends also on the stratification. So the stronger the stratification, the greater the density difference. Next. So we put this all in a numerical ocean model, and we blew wind over the model, and we did several simulations. So on the right is showing you a block of 9 simulations where we varied the wind and we varied the stratification. And we put a tracer in this model to see from what depth that tracer is upwelled. So in the left top corner, you see this tracer. This is an upwelling tracer. The more blue or white the tracer is, it means the water is upwelled from deeper. The more green the tracer is, it means that it was originally surface water. And so on the right top panels, you can see these 9 numerical simulations. The higher the wind stress and the lower the stratification, the deeper from where the water is upwelled. And the lower the wind stress and the stronger the stratification, water is upwelled from very shallow. And you can test this estimate that I just gave you using these model simulations. And we have an estimate of the source depth of the upwelling. And now we can look at the Arabian Sea and Bay of Bengal. And in the Bay of Bengal, the density stratification is much stronger. So the source water that is upwelled has a greater density difference than the surface water. But the depth from which this upwelling occurs, as we estimated it to be about 73 meters in the Bay of Bengal and about 200 meters in the Arabian Sea, suggesting that water is upwelled from much deeper in the Arabian Sea than Bay of Bengal. Next. So one other factor that determines the SST signal is whether the density is set by the temperature or the salinity. So we're looking here at both Arabian Sea and Bay of Bengal. And on the very right, I showing you a salinity profile for the Bay of Bengal and Arabian Sea. The next figure on the right is the temperature profile of the Bay of Bengal and Arabian Sea. And in the middle, it tells you how much the density offset is because of temperature compared to the salinity. So because you have a very strong salinity gradient in the Bay of Bengal, if you look at the second panel from the left, you'll see that when you have upwelling, about 50% of that signal or change in density is due to temperature. The other 50% is because of salinity. And that's one reason you don't see a very strong SST signal when you have coastal upwelling in the Bay of Bengal. In the Arabian Sea, on the contrary, you see that water is getting not saltier as you go down, but fresher as you go down. So when you upwell water, you have more than 100% signal in the density offset in the temperature. So the Arabian Sea is a great place to look at upwelling, and SST as an indicator of upwelling. The Bay of Bengal is not such a great place to look at SST as an indicator of upwelling. Next. Another factor that really determines the strength of the upwelling or the upwelling is the consistency of the winds. So these are showing you probability distributions in the Arabian Sea and Bay of Bengal of the wind stress. So if you look at event length, which is on the x-axis, and wind strength, you'll see that on the y-axis, you'll see that a certain wind event of a certain strength can last much longer in the Arabian Sea than in the Bay of Bengal. So the Bay of Bengal has very intermittent events, and that has to do with these monsoon intraseasonal oscillations. So the upwelling starts, but then it's very intermittent and it dies out. Whereas in the Arabian Sea, the wind stress is continual, and you continue to see the strong upwelling signal, which really spreads offshore, and you see a very broad band of upwelling. Next. So here, let's look at some images now. The top row is showing you Arabian Sea, and the lower row is showing you Bay of Bengal. So if I look at the bottom left plot in the Bay of Bengal, I'm looking at the SST. And if I look at the L3 product, then I can see that the signal of upwelling is right near the coast. It doesn't spread very far offshore. And when I look at the L4 SST product, I don't see that signal at all. And so you might ask, why is that the case? And that's the case, I think, because of cloudiness or poor SST. So I don't really know the reason, but the SST near the coast in the Bay of Bengal is very poorly resolved. And if you look at the L4 product, in fact, you cannot even see the signal of SST in the upwelling, even though you see a little response in the chlorophyll. If you look at the Arabian Sea, you see a very clear signal of upwelling. So both in the L3 and the L4 product produce a very nice clear signal of upwelling. And on the right, you'll see that the SST, the probability density, that at a buoy, we can see that right near the shore in the Bay of Bengal, you do see a response to upwelling with a 3-day lag from the wind stress. But if you look at the L4 product, it's completely missing the low SSTs. And I think that's because of the cloudiness. Next. So one additional factor that we should keep in mind in the Bay of Bengal is that if I look at winter SST, so this is in December, you see these nice cold filaments and in the northern Bay of Bengal. And I want to emphasize that these are not upwelling filaments. So this is not cold SST because of upwelling. In fact, this upwelling, this SST is cold because this mixed layer is very shallow and because it's still cylindrically stratified. Next. So the next figure shows you a schematic of what's happening in the Bay of Bengal. So you have these salinity fronts, and in the winter, this is very shallow mixed layer with fresher water at the surface, which is coming from runoff from the rivers. And when you have this cooling at the surface, you lose heat where the surface mixed layer is the shallowest. So right at the fronts where the surface mixed layer is shallowest, you have very shallow stratification and you get cold SST, and that has nothing to do with upwelling. In fact, it's a region of very strong stratification. Next. So I'd like to summarize just by saying that different regions, the response to SST, the response of the SST to upwelling is very different. But sea surface temperature is one of the easiest things to measure. In fact, we are planning to measure this from fishing vessels off the coast of Ghana. And we're trying to find the link between SST, wind stress, and then the biogeochemical response. And a lot depends on the physics of the region, on the salinity, as well as the temperature, on the intermittency of the winds, and the depth from which the upwelling occurs, along with the strength of the upwelling. So trying to take this apart for different coastal regions will give us a much better handle of being able to use the SST in a way to try to predict the biological response. Thank you.